Simcenter 3D is an ideal tool to help you predict performance of cooling systems for densely packed, heat-sensitive electronic systems. Simcenter 3D is an integrated multi-physics environment that can simulate tightly coupled 3D airflow and thermal fluid behavior without having to manually transfer data between solutions. In this demonstration, we start by importing ECAD schematic data using an associative bidirectional data exchange for printed circuit boards, otherwise called PCBs. This allows us to directly generate a 3D assembly of the board and its components. By pointing to a user database of component thermal properties, Simcenter 3D creates a suitable model for each electrical component. The copper trace data imported from the ECAD is used to compute and apply detailed conductive properties to the board thermal models. The PCB finite element model can then be added to this PC finite element assembly model and quickly be positioned into place. We then need to generate the internal and external air domains necessary for a thermal fluid analysis. In a typical CFD workflow, developing the fluid domains can be a very time-consuming process. However, with Simcenter 3D, this can easily be accomplished using a surface wrap algorithm that even works at the assembly level. In addition, we can choose to further refine the wrap by defining a tighter local resolution, in this case around the PCB. This flexibility ensures we produce a mesh that captures details only where needed and does not unnecessarily increase computation time. Because components of the PCB are close to those of the assembly, contact prevention constraints are used to ensure an adequate gap is maintained. All of these constraints can then be added to the surface wrap definition. And finally, the resulting fluid domain is associated to the base geometry. So in the event of a design change, you can rapidly update the fluid domain with little additional effort. The wrap automatically generates a 2D mesh, which is then used to only generate the corresponding 3D solid mesh. Again, the mesh is also associated to the design, so if the PCB design changes at any time, the wrap, 2D, and 3D mesh will always update automatically. Once the internal domain is generated, we can then generate the external air domain around the enclosure. We can then define a coupled multi-physics thermal flow analysis. We can also take advantage of high-performance computing resources to reduce solve time by selecting the parallel solver option. Because the CAE model is an assembly, we can quickly reuse existing boundary conditions. Here we can import previously defined boundary conditions for the PCB into the entire assembly FEM. This greatly reduces pre-processing time by not having to redefine the loads and boundary conditions at a new level. To complete this model, flow boundary conditions are applied at an inlet to represent forced airflow of 5 meters per second from the ceiling onto the PC, which would be rack mounted. The flow outlet would be on the floor, which is typical of a data center setup. It's then necessary to create a thermal coupling between the external air domain and the casing to ensure we properly model the heat dissipation from the PC. Once the model has been solved, we can view the results to see whether this nanobox PC dissipates the heat generated from the PCB or whether a redesign is warranted. We first observe the airflow is close to zero at the top flat surface of the PC, which is expected since the air from the ceiling hits the top of the box first. Then the air accelerates along its fins. We can then view the thermal results of the PCB and see that there is a high temperature of 51 degrees C, which is mostly localized on the board. The surrounding components, however, remain at the ambient air temperature, which indicates heat is being well dissipated even within the PC. This is confirmed when we look at the internal fluid temperature and see how the heat is transported away from the PCB inside the enclosure. While these results indicate the mechanical design will meet the operating conditions of this PCB, It is also possible to quickly create and evaluate multiple PCB design variants and compare the performance of each. With traditional CAE tools, this would be a tedious task that could take days, but through Simcenter 3D's fully associative analysis model, we can quickly update the analysis model to reflect each new design variant within minutes. Going back to the assembly model, we're able to replace a PCB component with a new board. When replacing the board, Simcenter 3D will automatically position the new board in the same location as the previous board. You can then observe that the error domains are out of date. However, by quickly redefining the surface wrap constraints for the new board, and then dragging and dropping the constraints into the error domain recipe, the wrap and resulting error domain get updated to the new design. Next, we re-import the loads and boundary conditions for the new PCB into the assembly model and resolve the model. Finally, we wish to compare the thermal performance of both PCBs, and this is easily accomplished by displaying both results side by side and interacting with them simultaneously. As you just saw, Simcenter 3D streamlines thermal flow multiphysics to help you predict how well electronic cooling systems will perform.